Hello everyone, welcome back to my organic mechanism talk. And today we will talk about 4 reactions together. Why we talk about so many reactions together? Because they are reactions of alkyl halide and they are basically competition. So we have to put them together. So this I show the alkyl halide. X means halide, fluoride, chloride, bromide, iodide. Although we actually most common halide uses chloride or bromide iodide. We don't use fluoride because that's not good leaving group. We call this leaving group. And there are actually four possible reaction. Two reaction is called a substitution, include Sn1 and Sn2. Usually you need a nucleophile here, and the substitution reaction will happen between the nucleophile and the leaving group. The nucleophile actually will kick off the leaving group, or you can say replace the leaving group to form the new product, and the leaving group will be the byproduct. And another possible reaction, I should say other two possible reactions are elimination. If you use a base, you could have elimination E1 or E2. Two type of elimination, and the product will be alkene. It's unsaturated hydrocarbons. And the byproduct will be the hydrogen halide. Okay, so now let's talk about a little bit more about the nucleophile here. And basically, nucleophile and base are similar. Strong base usually are good nucleophile. Okay, strong base are good nucleophile. There are exceptions though, but usually strong base and good nucleophile are Sn2 E2 conditions. That means good nucleophile you usually used for Sn2 reaction and strong base used for E2 reaction. This is to show some common strong base and good nucleophile for Sn2 E2: hydroxide, alkoxide, thiolate, amide, ammonia and amine, cyanide and acetylide. These are good examples of the strong base, at the same time good nucleophile for Sn2 and E2. Now weak base are poor nucleophiles, so they are Sn1 E1 condition. So that means poor nucleophile used for Sn1 and weak base used for E1 reaction. Example are water and alcohol. Exception is the T-butoxide anion in potassium T-butoxide, and this is a strong base but a very poor nucleophile because the very bulky group, T-butyl group in the anion, so it causes too much steric hindrance for substitution reaction. So that's why it's a very poor nucleophile. Now let's talk about the leaving group. Although we use the alkyl halide as the example of the leaving group, this can be other leaving group. We have different categories. First, the excellent leaving group include OTS, actually also can be OMS, and iodide and water. They are excellent leaving group. How to tell that? Weak base are good leaving group. The weaker base are the better leaving group. So it means these are very, very weak base. Now bromide is example of good leaving group. Chloride is not as good as bromide, so it's called a fair leaving group. Poor leaving group means they are pretty strong base, fluoride and hydroxide. They are poor leaving group. Okay, so now let's talk about the Sn2 and E2 reaction. I put them together because there's a competition between these two reactions. S means substitution, N means nucleophilic, 2 means 2 species involved in the rate determinant step. E2 is elimination reaction. E means elimination, 2 means 2 species involved in the rate determinant step. And actually, both reactions are called the concerted reaction, means just in one step you form the product. you can see the reaction example are shown here. The reactant is a propyl bromide. This is a sodium methoxide. It's a strong base and it's a good nucleophile. This reaction gives you two possible products. One is from the Sn2 reaction. The product is the methyl propyl ether. The elimination product, the E2 product, is actually propene and alkene. Let's look at the mechanism of Sn2 first. The good nucleophile, this is the methoxide, and this is the leaving group. This nucleophile, the methoxide, will approach to this carbon from backside of the leaving group and pick off the leaving group. In one step, you form this methyl ether as a Sn2 product. And the configuration of this carbon will also be inverted, or you can say flipped. So this is important if this carbon is asymmetric center. And the backside attack is the required for the Sn2 reaction. Now let's look at the E2. You may notice that I draw this hydrogen here. We call this carbon alpha carbon, which is connected to this leaving group. You can also notice that I move this leaving group to up, and this hydrogen is down. So this is called an anti-periplanar. In a 3D space, it's the anti position. And this is required for E2 reaction. So the base will depronate this proton, which is anti to the leaving group. Push the electron of the sigma bond to here, and then kick the leaving group off. So again, this is also concerted reaction. In one step, you form this propene as the product. So again, this carbon is alpha carbon. This is the beta carbon. So alpha carbon will have leaving group. Beta carbon will have that proton be deprotonated. So these two atoms, the leaving group and this proton, should be anti-periplanar. That's required. The Sn2 and the E2 also have a similar mechanism here, because the leaving group will always be kicked off by electrons from backside. Sn2, the electron comes from the nucleophile. E2, the electron comes from the sigma bond. But they all must attack or kick off the leaving group from backside attack. Now, this is an example of a primary alkyl halide. And usually for the primary alkyl halide, the Sn2 product will be more than elimination product. So if you want increase the percentage of the elimination product, you actually can change the primary to secondary or tertiary. So when you increase this steric hindrance of this carbon, for example, tertiary alkyl halide, will stop the Sn2 reaction, because if you have more steric hindrance here, then that will block the nucleophile. But for E2, it doesn't matter. So when this carbon is tertiary, actually the only product will be E2. Or if you don't want change the structure of the substitution, and you can change the base to bulky base like a T-butoxide. That will also increase the chance or percentage of the E2 product. Okay, next we'll talk about Sn1 and E1. E1. I use this tertiary bromide as the substrate and use this Sn1 E1 condition, this is methanol. And you could also have two possible products, Sn1 product, E1 product. And you may notice that I used example, it's a tertiary bromide. I didn't use the primary bromide. So now you will see why. Okay, let's look at the mechanism of these two reactions. First step of the both reaction actually is the same. It's a dissociation of this leaving group. This carbon-bromine bond or the carbon-leaving group, the bond just broken, and then form a carbocation intermediate. This carbocation in this example is a tertiary carbocation. It's a stable carbocation. So if you use a primary alkyl halide, then this will be primary carbocation, which we know that's not stable. That's why primary alkyl halide will not undergo Sn1 or E1. Okay, so tertiary will be preferred substrate. From this intermediate, this is actually a common intermediate for Sn1 or E1. So if you have the nucleophile, the methanol, it's weak nucleophile, poor nucleophile, but it's okay, it works for this Sn1, will attack this carbocation and form this protonated intermediate. Another deprotonation, the weak base deprotonated proton, and then will neutralize this intermediate and form the final product. It's another methyl ether. Okay, so now another possible reaction is E1. This is Sn1. E1, I will show this beta proton again, so this will be deprotonated by the weak base. The weak base deprotonated proton and push the electron of a sigma bond back and form a pi bond. So that will give you the alkene. That is the E1 product. Okay, so you can see from the same intermediate, and you can form this two product. Now, since this intermediate is a carbocation, so you have to watch out the possibility of carbocation rearrangement. If they can form a more stable carbocation, actually you should do the carbocation rearrangement. For example, 1,2 hydride shift or 1,2 methyl shift before you do the further steps. Okay, now to summarize the Sn1, Sn2, and E1, E2 competition, this is the principle. Okay, when you're considering the major product, stronger base will encourage more elimination product. That's first. Second, less steric hindrance will encourage more substitution product. Okay, so that's all I want to tell today. And if you have any questions, please let me know. Okay, good luck.